The Chemistry of Airbags by Catherine Badia, Han Yuang, and Shinara Marahachi. In the moments before a car crash, the only thing that saves us from our last fleeting moment of life is the chemistry of airbags. In modern-day society, airbags are currently mandatory in new cars as a supplementary safety device because of their success rate in saving lives. And although airbags are common and mandatory knowledge, we rarely think about the chemistry behind how they work. We wanted to investigate the mechanics behind how they function and share our findings with the class. Airbags are a mandatory supplementary safety device in automobiles used to protect passengers in a car crash. They were first patented in the 1950s but have been commonly available since the 1980s. Airbags have saved many lives, with the National Highway Traffic Safety Administration estimating that the combination of an airbag plus a lap shoulder belt reduces the risk of serious head injury by 85% compared with 60% reduction for belts alone.
Airbags are designed to inflate rapidly in the event of a collision and prevent the passengers from being ejected or flying into the vehicle structure. The airbag consists of a steel sensor that slides within a smooth bore. The ball is held in place by a strong magnet or stiff spring, which keeps the ball in place when a car goes over a typical bump. But when the car rapidly decelerates, as it would in a head-on collision, the ball moves forward and turns on an electrical circuit. Once this electrical circuit is turned on, there are a set of 3 chemical reactions that inflate the airbag.
This chemical reaction is known as a decomposition reaction, the idea that one reactant forms 2 or more products. This reaction involves sodium azide, which is a stable salt at ambient temperature. When the car is in a collision, the deceleration sensor signals a gas, known as the generator mixer, to create the high temperatures needed to heat up the salt, which leads to the decomposition of NaN3 into sodium metal and nitrogen gas. This leads to a release of large amounts of nitrogen gas in milliseconds.
The first reaction is meant to save the passenger's life. The following reactions, however, are meant to remove the sodium metal since it is not benign chemical. First, the sodium reacts with potassium nitrate to produce potassium oxide, sodium oxide, and additional nitrogen gas. The nitrogen gas generated in this second reaction also fills the airbag, and the metal oxide reacts with silicon dioxide in a final reaction to produce silicate glass, which is stable. Vehicle airbags work according to the ideal gas law, PV equals nRT, where P equals pressure, V equals volume, N equals the number of moles of gas, and T equals the temperature, and R is equal to the ideal gas constant. According to the ideal gas law, the 2 sides of the equation must be balanced, so adding moles of N gas from the heating of the sodium azide causes the volume to increase, which inflates the airbag. Once inflated, the gas cools down from the temperature of the air outside and begins to deflate. Health concerns of airbags. That's not the only chemistry involved. Notice that the other chemical into which sodium azide falls apart is sodium. Sodium is a very reactive metal that will react rapidly with water to form sodium hydroxide. As a result, it will be quite harmful if it got into your eyes, nose, or mouth. So to minimize the danger of exposure, airbag manufacturers mix the sodium azide with other chemicals that will react with the sodium and in turn make less toxic compounds. The silica that is the final product of the reaction can have major adverse health effects if breathed in the case that the airbag ruptures. Breathing in very small crystalline silica particles causes multiple diseases, including silicosis, an incurable lung disease that leads to disability and death. Respirable crystalline and silica also causes lung cancer, chronic obstructive pulmonary disease, and kidney disease. Exposure to respirable crystalline silica is related to the development of autoimmune disorders and cardiovascular impairment. Although there are risks and health concerns, airbags have been found to guarantee the safety of lives everywhere. The chemical reactions produced in airbags have created the safe and effective method of protecting passengers without causing more harm to them. It is necessary for the chemical reactions produced in the deployment of an airbag to be fast in order to protect us from collisions. It is also necessary that the chemical reactions between sodium azide, potassium nitrate, and silicon dioxide create a safe, effective, and fast method of cushioning the impact of an accident. Between 1987 and 2015, airbags saved 44,869 lives, demonstrating how major the safety development has been. Here are the discussion questions that we left for you guys.